Dear Dean Abart, dear colleagues, dear students, ladies and gentlemen, it's my pleasure to welcome you in this beautiful ceremonial hall at the University of Vienna, and I'm very happy to say a few words of welcome at the beginning. As you probably all know, but it's never enough underlined, hiring new professors is arguably one of the most important things we do at the university, decisions that have an enormous impact on the future of the universities. There goes a lot of work into the hiring process. It's a very high responsibility, but it's good work invested in the right things. Professors are obviously key to what we do here, so that is teaching and research. And every new professor shapes his or her field in a very personal way, but that does also contribute very significantly to the profile of his or her institute, his or her faculty, and the university at large. A good hire and a good fit for everyone makes a big difference for colleagues and students, and it does have an enormous impact on the future of the institution and its reputation. Inaugural lectures are thus a very important occasion, one could say a sort of rite de passage, to mark this important moment of transition when a new professor joins the University of Vienna, presenting some key aspects of his or her research work. And not just to a closed audience of specialists, but to the larger public. I know, of course, that the three professors that will present their inaugural lectures tonight are here for quite a while, so we know them already pretty well. They have already a big impact at the University of Vienna, and I think it's mainly due to the pandemic that we, had to wait a little bit before we can come to these inaugural lectures. But we are happy tonight. We are not getting one, we are getting 3 inaugural lectures. And I must say, by just looking at the themes and topics, 3 very, very different lectures, and at least in terms of theme and topic. So this looks all very interesting. So there is Professor Krzysztof Janowicz, Professor of Cartography and Geoinformation Science. There's Professor Kerstin Krellenberg, Professor of Urban Studies, and Professor Glenn van der Veen, Professor of Theoretical Extragalactic Astrophysics. So as you may guess, I will not venture into details of those research fields that are pretty far removed from what I'm usually doing in my own research, and I'm sure that Dean Abart will afterwards do so much better than I could ever do. But looking into the respective CVs of our 3 new professors, I think we can say that they all 3 do perfectly correspond to the University of Vienna's ambition to bring the very best people internationally to Vienna. Professor Janowicz joined us from the University of California, Santa Barbara, Professor Krellenberg from the Leibniz Institute of Ecological, Urban and Regional Development in Leipzig, and Professor van der Veen from the European Southern Observatory near Munich. Their respective research fields, as their lectures I'm sure afterwards, will show us also how wide and broad the themes and topics are that are united in the Faculty of Geography and it's such a complicated name, Faculty of Earth Sciences, Geography and Astronomy, which is of course an asset to have these days such complicated and diverse fields within faculties, because it brings together people that usually wouldn't even talk to each other. And I know about this because in this university we have excellent people all over the place, but it's very hard to get them to talk to each other across boards, outside the institute, outside the faculty, even more difficult. And it's not just a very broad range, as you can tell from the professorships I've just mentioned, but it's also an impressive range of methodological approaches dealing with critical models, with digital technologies, but also with things like social and economic impact or ethical aspects of research. And of course, as you all noticed from the program, the three topics announced for the talks also signal that the topics dealt with are of very, very big importance and relevance to society as well. So to conclude, I would thank all of you, even if you are here already for a while, for joining the University of Vienna, to making Vienna your new academic home. I hope after a few years you still feel good and feel that was the right decision. And we are very much looking forward to your respective lectures. And I will now hand over to Dean Abart. Thank you very much.
Ladies and gentlemen, respected Rector Schütze, dear colleagues, it's a pleasure for me to be here on this occasion to welcome three colleagues who relatively recently joined our faculty, and without doubt they add substantially to the scientific strength and the societal impact of our faculty. As the Rector already mentioned, we are not the largest faculty, but maybe we are one of the most diverse faculties at the University of Vienna. We are dealing with topics that range from the evolution of remote galaxies to the evolution of life. We look into the ancient past of our planet, into its current dynamics, and of course also into its future. I think as a society we have reached a point where the surface of the Earth is not only populated almost everywhere by our society, but it's also shaped by our society in a manner that is, let's say, has geological significance, enduring geological significance. That means we are arrived in the Anthropocene age. And our current actions, they not only shape or shift global climate, they also cause biodiversity loss at an unprecedented rate, and our activities force ecosystems and also society into very rapid transformations that eventually will be recognized as disruptive transformations when viewed over geological times. As a society, we are facing challenges, and to address these challenges requires that we do inter- and transdisciplinary research, and this is what we do at our faculty. We try to link approaches that are done by natural scientists, by geographers and earth scientists, with more global scale perspectives, and even with the extraterrestrial forcing from outer space, which is the key questions in meteorology and, of course, in astrophysics. We want to understand the risks and that come along with times of change, but we also want to grasp the opportunities and make use of the opportunities that also come along. And for doing that, we have to, and that's what we do, we integrate over all scales in time and space, and we do this in all spheres, the geosphere, the hydrosphere, the biosphere, the anthroposphere, of course, and of course, cosmos. Yeah, this is what we actually do at our faculty trying to find answers that we so urgently need in the interesting times we live in. But before we come to the answers that we give, I want to hand over something, or please hand it over to the rector, to our esteemed rector. This is just a documentation of what we do, and I want to make a connection to something that our rector uses to say. He claims that the University of Vienna is a hub, a stable hub of research and teaching, of student life and of culture, something to stand on, safe ground to stand on in the time of change. And we think that, we hope that you see that the beauty of the things that we deal with is also something to hold on. This is a calendar made out of pictures that have been taken by our students on their way into science when they do their first steps into research. And it's a very rare good. It's a limited edition. I have 3 more for this evening, and let's see how the evening goes and where they will end up. Thank you. So I was talking about the answers that our faculty gives, and the first answer that we have is Krzysztof Janowicz. He's professor for cartography and geoinformation science at the Department of Geography and Regional Research, and he joined our university relatively recently in 2022. He came actually from the University of Santa Barbara, where he was assistant professor, associate professor, full professor, and he also was the head of the Santa Barbara Center of Spatial Studies and the program chair of Cognitive Science program at the same university. He is co-founder and editor-in-chief of the Semantic Web Journal. And before moving to California, Krzysztof was assistant professor at the GeoVista Center at Penn State University. And before he went to the US, he was a postdoctoral researcher at the Institute of Geoinformatics at the University of Münster. And his research focuses mainly on how humans conceptualize the spaces and places around them. And neither me will venture on his research. I think he should do it himself. So please, the stage is yours. Thank you so much.
Well, thank you so much. I'm really honored to speak to you today about my research. My work that I'm going to present today is about why spatial is special in artificial intelligence research, and I will briefly start with introducing why I'm here, what do I give back to society. The core mission of my research is to understand how humans conceptualize the space around them based on their behavior, and I focus particularly on the regional and cultural differences in human conceptualization, with the ultimate goal of assisting machines to better understand the information needs of an increasingly diverse user base. That's a mouthful, it's a little bit abstract, so today I'm going to talk about the role of space and time in knowledge representation. So I hail from the faculty of exploration. Such faculty has three main pillars. We have the natural sciences, for instance, Glenn. We have the social sciences, represented today by Kerstin. And we have the data sciences, information sciences, represented by me. And I would like to use the next 50 minutes to show you that we all align very well and create interesting connections between us. Now, Glenn reminded me just half an hour ago that he works on galaxies, not planets. I know, Glenn, but I had to shrink down the scale a little bit. I will talk about planets. I know that Kerstin works on many very interesting questions in urban systems. I will just talk in relating myself to Kerstin's work about transportation networks. Only 15 minutes, only so much I can do. So, every domain claims they are special. And certainly you're all very, very special to me. But the reason why spatial data scientists and geoscientists claim that spatial is special is because of a handful of properties of spatial processes and spatial data that need to be taken into account to make sure we are analyzing spatial data in a meaningful way. I'm not going to talk about all of them that will fit or fill the next hour or two, only giving you two brief highlights. The first one is the so-called modifiable area unit problem. It describes the problem that if you take an observation, for instance, you're interested in crime density in Austria, then the result of this observation, for instance, a map that you may want to produce, will not only depend on crime, what you actually measured, but also on the level of aggregation of crime. And you can draw almost every map you like. My colleague Charlie sitting over there would say you can even lie with maps by choosing levels of aggregation to make your data appear as you would like to. The other one is spatial heterogeneity. It describes the phenomenon that things are not equally distributed in space. And jointly, these many properties of spatial processes and spatial data, they are so fundamental that they don't only apply to geospatial data, like in geography, but to other spaces. The space of the human body as studied in the life sciences, but also the spaces, for instance, that Glenn is studying. In fact, as was mentioned before, I was the director of the Center for Spatial Studies at UCSB, where we work together across the spectrum with people from the humanities, religious studies, even theater, because they all have spatial problems. Today I'm going to talk about an aspect that typically receives a little bit less attention, namely spatial and temporal validity or scoping. So let's take a step back and look at the big picture first. One of the most fundamental problems in all of data science and also what's called fair-based research data management is a very interesting, well, quite striking observation that data that is useful for any specific purpose tends to be less reusable, and data that is highly reusable tends to be less useful for any given purpose. That's a bummer, because data reuse, we call this opportunistic data reuse, is at the core of not only data science, it's also right now fueling the AI revolution. So what are the practical implications of this? Well, any given data science project, be this in industry or government decision-making, that does data science will spend roughly 80% of all of its resources, person power, time, money, on what's called data wrangling or data massaging, getting data into shape, cleaning data, collecting data, leaving only 20% for actually deriving insights. That's problematic. It makes data-driven decision-making expensive and likely to fail. There are many partial solutions for this problem. One that I think is quite dangerous as a solution is what's called data harmonization. And I hope in like 10 minutes you will know why. So what we really mean by data wrangling, data massaging is getting data into shape. And that sounds like a great idea. We are preparing data for analytics. But what it really means in everyday practice is that unfortunately most of us in data science are tool thinkers first. Namely, what we think for putting data into shape is, I have these tools, this is my favorite, for instance, machine learning toolbox, and now I need to kneel and cramp and cut the data into the right format. But with today's highly complex, heterogeneous, multifaceted, multi-perspective, multimodal data, that's doomed to fail. So we have this great slogan in machine learning, garbage in, garbage out, for instance. But in the domains that I'm involved in, for instance, humanitarian relief, I'm increasingly interested in studying conflicts, ESG and commodity trading markets. What actually is garbage there, and what do we cut and massage, right? So let me just leave you with one thought to make this less abstract. All the images in my talk are AI generated, and if you look closely, you may realize the second one has 6 fingers on each hand. Now I know biologically that is possible, but it's very rare. But it's common in AI imaging. And the idea why this is that we rarely see human hands like this or that depicted. We typically see human hands like this or that or that. And this lack of proper data that shows the whole dynamics of the human body leads to this kind of representations. This will be very important 5 minutes from now. Hold your thoughts. Okay, back to Kerstin's work. So road quality is a big concern, right? If you drive into a road crack, a pothole, for instance, you may break down your car, but most importantly, you may hurt yourself as a bike rider. In the UK, that's a very well-studied phenomenon. We don't know exactly how many potholes are there, but we know from last year, for instance, from the few local councils that reported road quality, that they fixed 1.4 million road cracks potholes, so there are plenty of them. So potholes are created typically in the winter or spring as a result of the soil and the pavement freezing and melting and freezing and melting. So that's the temporal component. But the spatial component of this story is that in the UK, the local council by law has to fix the potholes reported by the citizens within its administrative areas. So now, with what I told you about spatial heterogeneity, things varying in space, wealth, population density, so who uses the roads, weather, close your eyes and imagine how a map of road quality would look like in the UK. And you will get a map like one of these here. And now think what I told you before about, for instance, the modifiable area unit problem, that things appear one way or the other depending on how we aggregate this. All of these maps talk essentially about the same. The one that compares England to Scotland makes England look rather good. The one that is at the very bottom makes all of southwest England look like a really dangerous place to bike. The one from the government makes smaller distinctions, thereby painting a different picture, right? But that's not really at the heart of the problem that I want to talk about. At the heart of the problem is something like this. To report the pothole to the government, you need to first establish it's a road crack, it's a pothole. If you would like to do this in Gloucestershire, then you need to show that the road crack is a large dinner plate, large 30 millimeters, 300 millimeters, and the depth of a golf ball, 40 millimeters. If you would like to report a pothole in Worcestershire, you need to show it's a dinner plate, but a smaller dinner plate, luckily 20 centimeters in width, and a fist deep. And if you do this in Coventry, it has to be a pound coin and a 1p coin side by side. And the list goes on, there are like 100 more. So what I'm trying to tell you here is that where things are in space determines what they are, whether they are a pothole or not. And you may be thinking, what's with the Brits? why do we have all these many pothole definitions? Well, think about back what I told you about geography and the distribution of wealth. It happens so that the communities that require very large potholes before you can report them are simply out of money, so they don't want to fix that much, right? So you could also make a pothole map that tells you a lot about the wealth distribution in the UK. Okay, this is social sciences. I know what you think. Let's move over to Glenn. Things will be crystal clear over there, right? Well, not so fast. The original definition proposed on the 16th of August 2006 about what makes a planet didn't only include beloved Pluto, but also would have added 3 more celestial bodies now being called planets. But just 1 week later, the final draft agreed upon didn't only not include those 3 celestial bodies, but also demoted poor Pluto from the role of planet to dwarf planet. And this just shows concepts evolve through time, not always in the right direction, but mostly. Where's the space here? Because I promised space and time. Well, did you know that while Pluto passes through the night sky over New Mexico and Illinois, by law it's declared a planet? That's actually a fact. And I know what you're thinking. I'm happy to see you smiling. That's a quirky example for a nice talk. But where's the social relevance here, right? We are here to serve our communities. Well, do you know that there are 600 often legally binding definitions of what makes a forest? Good luck studying deforestation. And what about essentially contested concepts like migration? Okay, concepts are contested. Take-home message 1. But what about statements? So if you would travel now to India, open your laptop, open Google Maps, you would see one of the maps depicted here by the Washington Post. If you would then close your laptop, travel to Pakistan or China, open Google Maps there, you would see a different map of India, Pakistan, and China, because Google has many different maps depicting many different realities depending where on earth you open your laptop. That seems maybe like a minor detail to you, but keep in mind all statements about these countries therefore also need to be spatial temporally scoped. Next time you read, this is the overall area of India, this is the population of India. Well, according to where and according to when is that actually the case if the borders are not defined? Okay, time to wrap up here. Concepts and statements are spatially scoped. Why is this important? Well, unfortunately, our machine learning and also symbolic AI methodologies are not well suited for this messy world around us, because learning and reasoning in them are almost always strictly monotonic. Unlearning is really difficult for those systems, or in some cases not possible. So while there is some interesting work, and I happily go into the detail during the reception, we typically take another approach. We take the language of science that we are used to. We cast the problem of multi-heterogeneous, complex data as issues of vagueness, or measurement uncertainty, or fuzziness, like in fuzzy sets, or issues to be harmonized. But is this really a good idea? Because keep in mind, it's not that the government in India isn't sure about its borders. The border isn't vague. It's also not a measurement problem. If I stand here and I keep measuring, it's not that I wake up tomorrow and now I'm in Pakistan, right? So the problem is that oversimplifying this complex process leads to painting or leads to using a brush that is too broad and thereby reduces the diversity of data. And unfortunately, we know that data that is not diverse leads to bias in machine learning. The work that I'm doing here at University of Vienna and have been doing before is from the realm of what's called hybrid AI. We are combining both representation learning, so novel work from machine learning, with more classical, so-called symbolic approaches to come up with data structures called knowledge graphs that have this unique ability to handle multi-perspective data, even if data contradicts. I'm not going to go into any details here, but this is one such knowledge graph, one that we designed over the past 4 years. It's called the Nowhere graph. It's 15 billion statements, strong statements being facts, so to speak, so it has 15 billion facts across 30 different data layers, all tightly integrated, whether it's soil science, human vulnerability, highways, storms, or crops being grown, in a structure that is not only AI ready, but allows for more flexibility in different perspectives. I'm almost out of time, and I would like to close with the following thought and example, namely one more showing you that space and spatial thinking is really key to many domains. For instance, again, machine learning here. As you saw before, most of the images in my talk were AI generated. So it's fair to say, or to ask, where does the training data come from? Because it needs a lot of high quality training data. Turns out, if you study the spatial distribution of these data, only 3% of the training data that forms today's models, for instance, to generate imagery, comes from China and India combined. Let me put this the other way around. 97% of the training data for machine learning models in image generation comes from the United States, the UK, and the rest of Europe. Is that a problem? Does this lack of representing spatial distributions matter? Well, turns out it does. And there's a lot of work, novel work on AI fairness and AI bias that shows this across multiple domains. But we as geographers, we are not quite there yet. We just started a year or two ago with something that we call geography according to ChatGPT, where we ask ourselves, do we need to understand how those AI systems think about geography and geographic or earth science processes? So I would like to finish just with an experiment that we can do here together. I asked one AI to generate images just of forests, and the AI was free to generate whatever forest it liked. Here are two examples. You can see they look kind of alike. And then I asked a second AI to play a game of GeoGuessr with me. That's a game where we guess locations of images. And quite often it guessed for the images that the other AI created that those are the Appalachian Mountains in the US. Now that's anecdotal evidence, but I have an idea where this is going, and maybe you have one as well. Often AI and foundation models have been characterized as parrots, repeating what we are saying. But that's not a good analogy. They're more like distorted mirrors. And that may be actually good news, because many of us in the earth sciences and, for instance, cartography, know how to deal with distortion and how to make sure that we understand and can model those distortions. Well, thank you so much for listening. As you can guess, I'm the one who's doing the talking. Somebody needs to do the walking, and that happens to be my team. Thank you so much.
So we now move to an environment that we are all familiar with. Kerstin Krellenberg's work is focused on cities. Kerstin did her studies in Wächter in Germany, and then moved on for doing her PhD studies at Humboldt-Universität zu Berlin, where she also did her first postdoc. And from there she moved on to the Center for Environmental Research in Leipzig, with said Leipzig, to become a senior researcher. And then she moved on, sticking with Leibniz Institute for Urban Ecology, Urban and Regional Development in Dresden. And from there, she finally found her way to University of Vienna. She joined us in 2020 as a professor for urban studies at the Department of Geography and Regional Research. The focus of Kerstin's research is on cities, as I already mentioned, with a special interest in the sustainability transformations in urbanization. And this is what she will talk about, and the stage is yours, Kerstin.
Yeah, good evening. Also from my side, warm welcome, dear Rector Schütze, dear Dean Abart, dear colleagues, dear friends and family. It's a great pleasure for me to be here today and talk to you in this wonderful ceremonial hall. I will start my lecture with some personal words. I started as professor in Vienna, at University of Vienna, more than 3 years ago. It was in October 2020. Negotiations with the Rectorate took place in May 2020. We were already in the pandemics, so negotiations went on online. And I will never forget the pink-colored curtains in Rector Engel's private home. Negotiations went well, and I said yes. I said yes to Vienna, and I said yes to University of Vienna. The preparation of my move to Vienna started then in summer 2020. It was the pandemics, but everything seems to be manageable. I started to discover Vienna by city bike and recognize Vienna is quite hilly. Thus, of course, the move to Vienna also represented a disturbance to my life and to my family's lives. Long train distance traveling ahead. And there might also have been some kind of risk. I don't know, would it be the right decision that I made? I was at that time very confident that I would be resilient and able to adapt to the new circumstances. I was quite sure that I could bounce back efficiently and also maintain functioning, particularly with the certainty in mind that life consists of continuous adaptation processes, so I was certain that I would probably be able to adapt. But then the pandemic hit back hard, and some doubts came up. 2 days before my move to Vienna, Austria declared Germany a high-risk country. Would the moving company be able to cross the border? Yes, that worked. But my office was still under construction, colleagues mostly in home office, and then the assassination in Vienna's first district happened, and a few days later, lockdown. So my vulnerability increased, and I questioned my resiliency. I was fully in home office, students on black screens only. Recruiting of new staff members also resulted very challenging. And the only people I met in person were those in the supermarkets, at the local Saturday market, and those people at COVID test streets. But as all people, I started to adapt. I started to adapt to my new life, and continuously did so. And apart from adaptation and part of my move to Vienna, there was another tremendous change to my life and also my family's life, which I would call even a radical change or a fundamental change, and also a transformation. My life turned into a fully remote life. No family and friends around, no hugs, birthday celebrations only online. You remember that all. Thus, through continuous adaptation, my resiliency increased again, and this increase grew with the decrease of the disturbance over time. And there was some great relief over the summer 2021, when we started the first weeks of the winter term also in presence. But then, the next lockdown. All back to home office. Nevertheless, I would say more or less vulnerable because of the continuous adaptation that took place before. And what a relief to teach in presence then for the first time in summer term 2022, although still with masks. But I could get into touch with colleagues, with students, and also external partners outside university. Sorry, this was too quick. Overall, from 2022 onwards, things were getting easier, much easier, and I'm very happy that I'm here where I am today. Of course, the whole process, my start in Vienna, was not that linear as shown. There were many ups and downs, back and forwards, and also forwards again. But I'm very grateful for all the support I received over this time from family, friends, and colleagues. So I started my lecture with these personal words for good reason, and not because I wanted to complain. No, in no ways. The reason is that the story I just told you relates very, very much to my research, my work on and in cities. My work evolves particularly around the complexity of cities that has its roots in the many urban subsystems, the many imparallel ongoing processes, and the many actors that are involved in cities. And furthermore, the increased embeddment also in the globalization. So living in the urban age, cities are both drivers and also victims of global environmental change, mainly climate change, but also challenges like migration, demographic change, and also new technologies. I am particularly interested in how cities are impacted by climate change, what this implies for society and the functioning of cities, and how cities should and can develop in the future. I've done a lot of research on urban vulnerability, mainly in Latin America, to understand who and what and where in the city people are vulnerable to climate change. This knowledge is needed in order to respond with targeted adaptation measures that are context-specific. So adaptation to reduce vulnerability is rather a reactive than a proactive action. Examples are planting trees for greening or building protection walls to protect houses from flooding. With this kind of adaptation measures, it is thus still very difficult to address the many in parallel ongoing processes and interactions that are connected across spatial and temporal scales. For example, the increase of water that comes along when we have more trees in the city, or the redirection of the water if we have protection walls and someone else will be affected by the water. Thus, this is something that happens. It happens because cities are those complex adaptive systems that they are, and they are continuously adapting and changing. So I argue that adaptation should also be embedded in a wider and a broader framework that gives general direction to the overall vision of the cities of the future. That's a vision like sustainability that includes normative targets and aims at well-being and also an equity with regards to the contribution of services, for example, energy provision, water provision, also the accessibility of green areas, and also affordable public transportation. The often mentioned and also controversially discussed Agenda 2030 with its 17 development goals provides such a normative framework. Although with challenges of how to break this down, these targets that have been developed at the global level. So what does this mean for cities? This is also something I'm doing work on. Given that governance and administrative structures of cities are also questioning the way of how to apply such a holistic, sustainable view on cities. So driven by the fact that cities developments are often unsustainable and that incremental changes like adaptation are not enough in order to deal with these grand challenges that we are facing on. The many interrelated processes, we argue and I argue that we need more fundamental changes. We need fundamental changes, we need radical changes, and those have to go at the roots of the problems, and these changes need to tackle infrastructures, lifestyles, and also governance structures. And those changes are called transformations. But what does this mean for the resilience of cities? I argue that in order to remain functioning, as the example of the pandemics has shown, under new conditions such as higher temperature as well, transformations are particularly needed. And I thereby acknowledge that resilience is non-normative and also an attribute of the city. And it's neither good or bad if you are resilient or not. Because a city might be resilient, but locked into a totally undesirable system. And then the situation is stable and resilient, but the situation is unsustainable. So the idea is about how to develop alternative configuration. And the resilience framing in this sense can guide also management and planning towards more desirable sustainability, stability, and also the functioning of cities. It's very important that cities follow up very different pathways. And transformations might be possible in one city, but not possible in another. Always the context matters. And all cities, or each city, needs to develop its own trajectory. In this regard, I see sustainability as the target of a transformation with the aim of desirable resilience. And all this goes hand in hand also with the aim of unraveling the power of cities to contribute to global sustainability, and also the mitigation of unsustainability and climate change by transforming. So through my work on both transformations and sustainability, I mainly address urban sustainability transformations in order to develop cities worth living in and for. So these last minutes were a bit tough conceptually, but this is what I also do. I try to develop this way of thinking further, what the different terminologies mean, in order to bring more insights on what the different things mean and how they can be also looked up together. So this is mainly urban sustainability transformation, that it's my focus. What is an urban sustainability transformation? Or what can be a transformation? One fundamental transformation might be to decide we are now a 50-minute city. So the example of Paris that is followed up by the mayor of Paris goes in that direction. So when we think about that all basic services would be provided only in 50 minutes distance from people, this would, of course, lead to less traffic, less emissions, and also providing possibility to use the open space in different ways. So we could think about a multifunctionality of the space that is available then. Another example for such radical urban sustainability transformations are circular cities. You all know about circularity. The notion is not new, but it's again new on the agenda. And the circular city promotes the transformation from a linear to a more circular economy by minimizing resource input and waste, and also emissions by closing energy and material flows. For example, aiming at repairing, reusing, also remanufacturing and recycling materials, with the overall aim to increase resource efficiency. So we are interested in how this concept, the concept of urban sustainability transformations, can be applied, and also particularly investigating the interlinkages of the different social, environmental, and technical aspects that are involved. But if you imagine a circular city, you need natural scientists and social scientists working together and fully understand the potential. And this, of course, again, with the overall aim to increase sustainability in the long run and to enhance desired resilience. So a lot of research is still needed to unravel particularly the implementation possibilities of these approaches. This is theoretically fine, and there are many ideas at hand, but how to implement that? These fundamental changes are that's what we need, but how can we get there? In order to understand this and to increase sustainability in the long run, we have to do much more research. And what I argue that for that, we have to leave the ivory tower of research. What we have to do is to work much closer together with society. We have to tackle the real-world challenges and also involve the many urban actors that are taking part in those transformations that we need. These are politicians, that are people working in administrative or also planning institutes at the city level. And of course, it's about the civil society. And for that, we need more transdisciplinary and also transformative research in order to do this. And we need to think about how we can jointly work on that. There, the notion of co-designing and co-production is very much in the forefront. So working together and producing knowledge together with the different actors. It sounds easy, but it's not that easy, because we have to bring together those actors. We need to raise their interest, and we have to listen to them. It's a lot about communication and how to do that. And why we do that? We do that because we see the great benefits when we include people in our work in order to work and understand the adaptive and transformative capacities that are involved. Therefore, in my research working group, we developed or established the Urban Sustainable Living Lab. And this lab, first of all, serves as a platform, a learning and exchange platform, in order to shape and also support sustainability transformations. Here we are working on, and we are very much looking forward to also fill this with more life in the years to come. Another example is that we also work on comparing and learning from cities all over the world. What you can see here is a map, just 1 year, when we had our 44 cities master students that are joining us each year in Vienna. And we work with those students also on their sustainability, on the profiles of their sustainability profiles of their home cities. That's what I wanted to say. So we have an enriching also information coming from our students. And with a new master program that we are now going to develop on urban sustainability and planning, we are also hoping to develop this even further. And maybe just on a side notion, we are now also getting more into third-party funding projects, and there's a new project to come up where we're going to look at the sustainability of post-industrial cities in Armenia. So this also will enrich our understanding and the conceptual framing of urban sustainability transformations. When I say me and we and us, I mean this wonderful working group. I'm very happy that all of them are here tonight, so this is also great. Thank you all for your support and your great work. It's a pleasure to work with you together. So, coming to an end, I'm convinced that through research we can contribute to develop cities worth living for and in, but collaboration strengthens us. So I'm looking very much forward to new collaboration, also within and also beyond the faculty. And I think what is key is that we need you all, as individuals, as citizens, We need to know what makes cities worth living in and for. So I started with some personal words and would like to end now also on a personal note. January 11th makes a very special date for me and my family and also close friends. My thoughts are therefore with a beloved person who supported me in my life long, but unfortunately couldn't see me becoming a professor. I'm all the more thankful that my mother can be here with me tonight, as is my partner Friedrich, also Sigrid and Henning, also Mrs. Krabisch, and I'm very thankful for all the support I received from you over time. And of course, thank you very much to Christine, to Darina, Carmen, and Andreas for the wonderful music. Thank you very much. Thank you all.
So now in our third talk, we will look beyond the fence. We will look into the distant past of remote places, and this view will be given by Glenn van der Ven, professor for extragalactic astrophysics. Glenn did his studies at Leiden University, where he studied both astronomy and mathematics, and he also obtained his PhD in astrophysics in astronomy, in Leiden University. He then moved as a postdoctoral researcher to Princeton University, and he was also a Hubble Fellow at the Institute for Advanced Study, USA. He was then a research group leader at the Max Planck Institute for Astronomy in Heidelberg, Germany. And then he won an ERC Consolidator grant, which brought him to the European Southern Observatory near Munich. And from there, we managed to get him here to Vienna, and he joined our faculty in 2019 as a full professor at the Department for Astrophysics, which he currently is also leading. Glenn's research focuses on the understanding of the dynamics of and structure and evolution of stellar systems, ranging from stellar clusters in our Milky Way and nearby elliptical, elliptical and spiral galaxies, and I'm sure he will tell us what this is. Yeah?
Thank you.
So thank you all for being here. It's really great to see such an audience. And yes, I hope to bring you the excitement to share with you on a topic that excites me already for 20 years. And this is related to the title of the topic. So I hope you will at least go away understanding galaxies and how they look like, and why we here with the group and collaborators are really excited about this. So not Houston. Yes, perfect. Good. So first of all, so what I wanted to address to you is the diversity of galaxies. So first of all, then I should show you some really wonderful pictures of galaxies. So we are in a unique position in astronomy that we have fantastical technical development, and one of them is the Hubble Space Telescope. And the Hubble Space Telescope allows us to really zoom in and look at these nearby galaxies, and the nearby is, thanks for alluding to that, is really for us astronomers is really almost in our face. So this is what we would call really the local universe. I will come back to what far for us means. So here you see such a majestic spiral galaxy. And you already see that galaxies don't live in isolations. This has a neighbor. This is actually a galaxy that's interacting. And here is another galaxy. And this is called some Prero galaxy. So you see astronomers can also a little bit imaginative. What you see here is on the side this spiral galaxy. But you see in the middle, you see this what we call a bulge. So this fuzzy ball of stars. And then there are actually giant galaxies, really, really massive, the largest, which are just this fuzzy ball of stars. And so these are all pictures from the Hubble Space Telescope, and since recent, you might have heard in the news, we have also the James Webb Telescope, which is a fantastic instrument, and this was one released deep field from the James Webb Telescope, and aside from the twinkling stars, that are really the nearby stars from the Milky Way, most of what you see here are actually galaxies. And this is what drives me to this question, how did galaxies evolve to become so diverse? They all look different, different shapes, different colors. And so this you can also sometimes phrase as, if we look at galaxies today, we call them a galaxy zoo. So, and here also comes a little bit of personal background story, how I actually came into astronomy. Because as you already heard, I also studied mathematics. And actually, mathematics was the one thing that I really loved in high school. And I loved to do mathematics to solve puzzles. But then there was my grandfather. He was a house painter, no higher education, but he was always going through the weekend science part of the local newspaper. And so what he did is then we came visiting him, and he kept asking questions, explain this, why is this, etc. And around the time I was in high school, the Hubble Space Telescope had this mirror fixed. It was a big issue. And then there were in this newspaper all kind of fantastic pictures of galaxies. Some of them I showed you. And my father had cut them out and put them on the table and asked me, okay, good. I didn't have the opportunity, you have good education, you seem to like problems. Why don't you explain to me, why are these galaxies all so different? Why did they look like? And that actually got me into astronomy. That decided, okay, good. And that's, with the long path, actually brought me also here today. And I'm really, really happy to be here at the University of Vienna. And I will try not to bore you, but give you a little bit of how close did we get to answering this question? We are not there yet, I can already tell you, we don't know yet. Yes, there's still many open questions, but we're starting there. And so one way in astronomy, and this comes now by what we mean really nearby and far, one way in astronomy with these fantastic instruments, what we can do, we can look at galaxies further away. And why do we are so excited about galaxies looking further away? Because light takes time to reach us. This means the further away we take, the more back we look in time. Wait a moment, the question was, how do galaxies evolve? That means if you look at galaxies further and further and further and further away, we look back in time. And actually with these telescopes, it's really possible to get very, very close to where the universe started and to see the first galaxies form. And this is what you see here on the left side. First of all, you see the I think the obvious thing, these are smaller. Yes, because galaxies actually grow over time. They accrete material, they merge with each other. But what you might also see there is a change in color. And this is because of the stars that live in galaxies. And in the early universe, young galaxies, there you have mainly these giant stars. But these giant stars, they die relatively quickly. Relatively quickly is for astronomers 1 million years. But sun-like stars, luckily, they survive for gigayears. And that is, but they look more red, and that is, or yellow, that is what you see to the left side. So this means there is more into than just these images. There is also something, if we can spread out, what is also called wavelength, from the blue to the red. And there we have a tool which is called spectroscopy. So you might, from the picture above, remember experiments that you have seen or done yourself, that you can with a prism spread the light, from really spread it out from the red to the blue. And this is also what astronomers do with the spectrographs. What you see here is an actual scientific, this is a galaxy, and you see the distribution of light in the wavelength. But the obvious point that you can immediately take out of it, it's not boring how it varies over wavelength. There are these lines going up and with blue labeled, and there are lines going down actually. And this is because of the stars. These stars and the gas in galaxies also, they have a certain chemistry. And this is what we can do with the spectroscopy. We can actually figure out what type of stars are there in galaxies. And that brings us back that we can figuring out how did this galaxy actually come to be. There's more to it, because with spectroscopy, if you now imagine that these lines, yes, you project them, and these lines, you have a nice broad spectrum from yellow to red, but these lines actually make these black stops. You would say that's not so nice, but it's actually nice, because if you measure precisely where these lines happen, then you can actually also measure whether they blue shifted or whether they actually red shifted. And that represents the motion of the stars in these galaxies. And if you do that, nowadays, for like 2 decades, actually when I started my PhD, this was really the hot new thing, is that we cannot just get a spectrum for one galaxy, one spectrum, but we can actually get a spectrum nowadays at every position in the galaxy. And so here you see an example from the Very Large Telescope. It's the instrument is called MUSE, and it's an instrument that we are using a lot. And so if you can get a spectrum at every position, that means you can also measure the motion at every position. And that is what you see on the right. Then you suddenly see that this galaxy in light, which like stands still, is actually moving. The stars inside are actually moving. So the red is stars coming towards us, and the blue is going away from us. Okay, you would say, fine, why such a big fuss about this? Well, actually, movement of things is sensitive to all mass. That means if there is dark mass, and you know dark mass in the forms of, for example, black holes you've heard of, but there's also, we know pretty sure that these galaxies are actually embedded in a so-called dark matter halo. This means if we can use these motions, we can also get a handle on what's called the dark side of galaxies. So the black holes in the center and the dark halo in the outer part. But we need dynamical models. And I will come back to that, because that's the tool that we do in our group and with the collaborators. So let's remember the spectroscopy was just not for the motions, was also for the chemistry. So now we can really map out the type of stars that are in this galaxy. So we have the motion and the stars, and these stars actually remember where they were born. Yes, because depending on galaxies merge, and if they were born in a smaller galaxy, there will be different stars with different chemistry than if they were born in the main galaxy, in the host galaxy. So we can combine these motions and chemistry as fossil records to really figuring out how they build up. Again, to infer, that's what we call the formation history, we need, or we want to use dynamical models. Okay, now I mentioned twice, at least dynamical models. What does this mean? What is the tool that we're using? And I try to explain to you this, and I know that you see that I'm not used to PowerPoint. So what you see here is, I will play it, is a movie of orbits, and stars and galaxies move on such orbits. And you see it just two, the green one and the red one. And what you see here is a model. That's what in our group and with collaborates, what we built. And because it's a model, we can look at it from every side. So the top view is the side view, the bottom view is the face-on view, or from above. And you see this red one is going around in circular orbits and is staying in the plane. Yeah? So we as astronomers learn from this that this star probably formed in this disk plane and is relatively young. So the key point here is that we make these models by calculating such orbits for thousands to a million of possible stars. And then we're figuring out those orbits that are helpful to explain all the observations. And just to give you one example, here's to the side is another example. Now you see added a blue orbit. Why? Because this blue orbit actually goes against the other orbits. It's a so-called counter-rotating orbit. And we astronomers then say, oh, wait, that's not how it normally should happen. There's something special that happened to this galaxy, because this is not normal. So this brings me to the current, to where I'm really proud of is that this technique that we have developed over the last 15 years, and our two collaborators, Maria and Jesus, sitting here, who has been really instrumental to this, and the University of Vienna, as a professor coming here, really gave me the possibility to bring this tool here and to build a group around it. And so I'm really proud having this fantastic group and the collaborators. And in this group, these are PhD students and postdocs, and there's also a software engineer. Why? Because we actually decided we will make this code publicly available. There was some use and reuse by mentioned, so we want other people to be able to do the same nice things. And making publicly available is a lot of effort, but within the University of Vienna, this made us possible to do it. So what are the next steps to finish up? So if you want, I would say I would have two visions, two dreams, yes? So one is actually coming back to my grandfather's question, yes? Did I answer this? Did I now know what really diversity is? And the answer is not yet. Why? Because the data that we use is very big. Yes, there are some numbers here. Yes, and then the models that we run. Yes, they are actually computationally very intensive models. We have a Vienna scientific cluster here. You can check. We are happy to use it. So the combination of the data and the models, yes, means if we really want to do more than a few galaxies, so really answering the full diversity, we will have to do something more, yes? And this is what we are looking at, new directions, also in the direction of machine learning. And what I'm also really happy about is that we branched out to mathematicians. And so mathematician Linz and the university here, we are closely working with them together, and we are also now all of this combined. We are happy that the National Funding Agency allowed us to group these people together in what is called the tomography across the scales. You might ask, tomography? Yes, the idea here is that we as astrophysicists, but physicists and people from medicine, so medical university, we actually sit together, we talk to each other, we listen to each other. As Kirsten was saying, it's not easy, yes? It took us actually really a long time to actually understand some of what we are saying to each other. But the nice thing is I think this effort is really beneficial. Because, for example, with the mathematicians, we are already making new progresses. So, and then one of the visions for this is really that we want to use the tools that are developed within astrophysics actually to transfer them also to other disciplines. And there is already a very nice example. Adaptive optics, which is used in astronomy, is now also used in OCT and optical coherence tomography. So this is not just like a dream, this is actually possible. And the second vision is something is even longer horizon. So the gravitational waves, you've probably heard about it. So this is really a new messenger, as we call it, a really new probe that we astrophysicists are really excited about. Yes, because for example, it gives us really good handle on black holes. And if we come back to the dark side of galaxies, this is really exciting. And that this is a really forefront field. So there was also recent the Nobel Prize in that. And so in my vision, what I think is that as Austria and also the University of Vienna, we really have an opportunity to step in here with one of the instruments that have been designed, and is called the Einstein telescope. We're talking about 15, 20 plus years from now. But now is the time to get in. And why is this so exciting? Because this is not just astrophysics. This needs physics, obviously, but actually you may see from the picture there are tunnels down the ground. So this is actually, you need to dig down 200 meters, you need to make tunnels of 10, 20 kilometers long. And then you see immediately, wait a moment. Then you probably also need some geophysics, some geoengineering, and this is where I think it gets also really exciting opportunity for Austria. So on that path, so we managed as a next step to actually get a summer school on gravitational physics in Vienna. And this is also included here, and there we'll finish, is our doctoral school. VISES, Vienna International School for Earth and Space Sciences. And I want to finish the personal words. When I came here in Vienna, one of the things that I was really excited about is actually getting a doctoral school. And it turned out to be that when I arrived here, there were several colleagues that shared this excitement. And within the pandemic, we managed to really build up this doctoral school within this faculty. And we already heard very nice word. It's a diverse faculty. But I think the diversity here is really an opportunity, because you really see, especially the young minds, that when they really talk to each other, even if they're from very different fields, it's to the benefit of them, and I think in the end it's to the benefit of all. And with that, I really would like to thank you all and all the people that are supporting this. Thank you.
So, ja, mir bleibt jetzt noch ein paar abschließende Worte zu sagen. Vielen Dank an, sorry, I should speak English. Some closing words. Thanks very much for our recent young professors. I think you convincingly showed that there is no lack of ideas, no limits to the phenomena we are studying, and there is no limits to scientific research and no limits to bringing this into society. I think you really made this clear, and we are very happy to have you here. And certainly you qualified as number 2, 3, and 4 to receive to receive the FGGA calendar. So. I think you everyone have realized that we are a diverse faculty, and it's sometimes difficult to find a common language. Yeah, we are from social sciences to astrophysics. There's a long way, but we are keep talking, keep exploring new territory, and I think this is where we want to go. Thank you very much for coming, for being with us for this wonderful evening, and I hope you can go on with talking, and I am happy to invite you on behalf of the 3 recent young professors for the reception that is prepared for you just next door. Thank you very much.